Okay, now we've talked about stress, and I said that that stress is going to cause a change in my material. Like I said, if I apply a compressive stress, it's going to get shorter and fatter. We didn't talk about getting fatter, but it will happen. Everybody gains weight. And if I try to apply a tensile stress, then it will get longer and thinner. That didn't actually draw longer. There you go, longer. So there's been some change. It was one length, and now it is a different length. It was some length, and now it is a different length. Now, strain is how we talk about this, but why do we talk about it in terms of strain? Well, it's very, very similar to when we're talking about stress. Seeing that a mountain can hold a load of 10 pounds isn't all that interesting. Like, okay, a mountain, yes, the mountain can hold that 10-pound block. Wonderful. That's why do I care? No, that's not all that interesting. But if I told you that a strand of spider silk could hold a 10-pound block, you would be amazed because, well, it's the difference in area. So one is feeling no stress at all. This is a giant cross-section. It's huge. This one, though, is a tiny cross-section. It's a tiny area, and yet it's still holding 10 pounds. That's amazing. So we wanted to normalize something. We wanted to normalize things to say, hey, this is an amazing material. So similarly, we're talking about when it stretches or compresses. How we tell if something is able to stretch a lot or not stretch a lot. Because if something is 10 miles long, and it happens to be able to stretch a foot, okay, that's interesting. It changed a little bit. Cool. But if something is a foot long and it's able to stretch a foot, that's able to stretch a lot. That's a lot of stretching ability. That's like rubber. If I make a metal that can do that, what in the world? That's incredible. So what we do is we look at things in terms of strain. Okay, we look at things in terms of strain. Strain is simply a way of normalizing. It's a fraction. It says, well, I've deformed, and that's a fraction of my original length. So for metals, it's usually really, really small, the strain is. But it can be bigger for rubbers. So if I was 10 inches long, and after I apply a load, I'm suddenly 11 inches long, well, that's a difference of 1 inch. And so my strain would be equal to 1 inch over 10 inches. Okay? It's a fraction. I've stretched 10.1 of my original length. If I multiply by 100%, I would get that was a 10% stretch. A 10% stretch. So, that's pretty amazing if that was a metal, or terrible. It depends on your application. You don't always want things to be able to stretch. Sometimes you want things to fail before they move like this. But that's beside the point. Second thing you need to realize is that this is unitless. Strain is unitless. The units cancel. Sometimes they say like inch per inch or meter per meter. That is simply just so you have something to talk about with a number. Because it's just weird when you say, well, it has 3,560 times 10 to the negative 6 strain. The strain is that. You're like, oh, wait, what? Also, you might hear people say strains. That's done just so we can actually have a nice little symbol to attach to it. But that strain is just reminding you that it's unitless. Okay, so no units for this. It's just a fraction. And it's a fraction that is telling us how much a fraction of the original length has it stretched or compressed. Okay, has it stretched or compressed. As a note, strain will be positive when it stretches. It will be negative when it compresses. So that's it for this time. Thank you so very much. And I'll see you all next time as we try out an example. Have a wonderful day. Bye-bye.